Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be doing a calculation or a couple of problems of how to find the pH of a buffer solution. So I'm going to have two problems here. So in the first problem you are given a buffer solution of the acid and its conjugate base where you have 0.1 molar of each. And here they happen to be the same, but they don't have to be the same. They could be different. It works the same way. So the first thing you want to do is set up an equation and your ICE table for the equation. So you're going to have your equation for the acid. So HC2H3O2 aqueous plus water liquid is going to then go to the H3O plus aqueous plus C2H3O2 minus. And so that's the equation that we are going to be using. And then you do your ICE table like you normally do. But here the starting concentrations are not going to be all zero over here. So here we're told we have a concentration of this acid here of 0.100 molar, so we don't need to write the molar down. And here the starting concentration of your H3O plus is effectively zero, so we're going to put 0. And then, of course, here we're told that we have a 0.100 molar solution of that ion, so it's 0.100. And then you're going to do the change. So the change is going to be, you're going to lose some here, so negative x, it's all 1 to 1 to 1 ratio. So negative x, and then you're going to have, you're going to add some of your hydronium ion, and you're going to add some of your anion. And so then we add these together and you get 0.100 minus x. This is plus x, and this is 0.100 plus x. And then we're going to use our equilibrium constant. So this is going to be Ka is equal to 1.8 times 10 to the negative 5. So 1.8 times 10 to the negative 5, and that's going to be equal to these concentrations. So H3O plus multiplied by the concentration of C2H3O2 minus, all over the concentration of the acid HC2H3O2. And so all we need to do is put 1.8 times 10 to the negative 5. We're going to put our equilibrium expressions in there. So here we're going to have x. So x times 0.100 plus x over this expression, 0.100 minus x. And then we can do the x is too small approximation to simplify it, and then we'll check to make sure that that approximation is valid. So we get rid of the x's. And so when you get rid of the x's, it's just 0.100 over 0.100, so that cancels out. And so x, 1.8 times 10 to the negative 5, ends up equaling x. And so then what you can do is you can then take the x, 1.8 times 10 to the negative 5, divided by the original concentration of your acid, 0.100. So 0.100 times 100, and you get 0.018%. So you get 0.018%. So this is less than 5%, so it's a valid assumption. So the x is too small is a good approximation. So now that we have x, well, we need to find the pH. So we have x. X is equal to the hydronium concentration. So all we have to do is take the negative log of this number. So notice we have two significant figures. So if we take the negative log of, so we'll take the negative log of 1.8 times 10 to the negative 5. You take that negative log and you get 4.74. So the pH is equal to 4.74. And again, notice that when I take the log of 1.8 times 10 to the negative 5, I have two sig figs here that translates into 2 decimal places, so 4.75. Okay, that's how you find the pH of a buffer. Now, what if instead of giving you concentrations, they give you volumes and concentrations of two different solutions and you mix them together? Well, in that case, you're going to have to recalculate what the concentrations are for each species. So you're going to have to recalculate the concentration of this species, the acid, and its conjugate base. So that's the first thing you need to do. So if we go ahead and do this, so we have 60 milliliters. If we convert that to liters, we have 0.0600 liters. And over 1, if we use this as a conversion, we get moles. So that's going to be moles over liters, so 0.250 moles per 1 liter. Liters cancels out, and then you get moles. So 0.6. Okay, so 0.0600 times 0.250 gives you 1.5 times 10 to the negative 2. So this is 1.5 times 10 to the negative 2 moles of HCHO2. And then we do the same thing. So we've got 15 mils, that's going to be 0.015 liters. And then they gave us 0.5, so 0.500 moles over 1 liter. Liters cancels out. And you get 7.5 times 10 to the negative 3. 7.5. So you get 7.5 times 10 to the negative 3 moles of the conjugate base, so NaCHO2. So now we have the moles. So now all you need to do is recalculate, take the moles and the volume. So you add 15 milliliters to 60 milliliters, or 0.06 liters and 0.015 liters. Add those together, that'll be the total volume. And then you divide that by each of these. So the total volume is going to be 0.075. So you take this, divide it by 0.075 liters, take this, divide it by 0.075 liters, and you're going to get your new concentration. So this, so it's 1 times 10 to the negative 1. So this becomes 1 times 10 to the negative 1 molar, or in other words, it would be 0.100 molar. And then for this one, it would be, that would be 0.2. So this one would be 0.200 molar. Okay, so now that we have the new molarities, now we can do the same thing we did in our first problem. So then we're going to erase the board. So we got this. Okay, so let's give ourselves some space. Okay, so let's do our ice table. We'll do our ice table, and we're going to do the initial and final. Let's write out our equation first. So we have CHO2 aqueous plus water liquid. That's going to give us H3O plus aqueous plus the CHO2 minus aqueous. And so we have our ice table. And so the initial concentration is going to be for the acid 0.2. So we got 0.200. And for the conjugate base, it's going to be 0.100. Okay. So now this is going to be practically zero, no hydroxide or hydronium ion. So then the change is going to be negative X here, and then we have positive X here, and then we're going to have positive X there. And so when we add these together for equilibrium, it's going to be 0.200 minus X, and then this is going to be plus X, and this is going to be 0.100 plus X. And then we have our Ka value for the acid, which is formic acid. So it's 1.8. So this is 1.8 times 10 to the negative 4. And again, this is going to be equal to the concentration of H3O plus times concentration of the HCO2 minus CHO2 minus over the acid, which is the concentration of HCHO2 2. And then when you add in 1.8 times 10 to the negative 4, you're going to substitute these values in for here. So that's going to be equal to X times 0.100 plus X over 0.200 minus X. And then again, you could do the X is too small approximation. And so you do that, get rid of the X, and then you've got 0.100 divided by 0.200, and then you can solve for X. And you get 3.6 times 10 to the negative 4. So X is equal to 3.6 times 10 to the negative 4. And so what you could do is divide that by the concentration of your acid, 0.2, multiply that by 100. You'll find that it is validated by the 5% rule. And then X becomes the H plus concentration. Then you take the negative log of that, and you are ready to go. And you get a pH. So pH is equal to 3.44. So I hope this is helpful. If you enjoyed the video, like, share, subscribe, hit the notification bell.